moving right along. This will take forever if we don't stop at some point, right? But okay, we're going to finally get something interesting, k equal 2. Okay, so then m is equivalent to n mod 2. What does that mean? And what's another way to say something is divisible by 2? Yes, m minus n is even. Okay? So, let's now start to look at some, this is a little more interesting, right? So let's start with 0 bar. So this is the set of all m, an element of z, such that, what? Okay, these are all things that are equivalent to 0. So how do I write that out?
M is even.
Okay, close. I mean, you're right, but let's do one more step. M minus 0 is even. But what is that exactly then?
Where m is even?
Yeah, that's actually equal to 2z, even integers. Okay, so the equivalence class of 0 just takes all the even integers, right, and puts them in one set. Now remember, equivalence classes form partitions, right? So they take a set and they divide it into subsets, and those subsets never overlap, right? If they intersect, they have to be the same. So take a guess at what might be another equivalence class. Okay, well 1 bar definitely will be in a different equivalence class. Well, 1 bar will be a different equivalence class because it's not even. Okay, yeah, so we're thinking, yeah, maybe there's only 2 equivalence classes here, right? And one equivalence class containing 1 is probably the other one, right? So let's just check that. 1 bar equals a set of all m, an element of z, such that m minus 1 is even. But you don't need to do a big calculation. I mean, we've already dealt with even and odd enough. That's equal to the set of all odd integers. Okay, so z mod 0 had infinitely many equivalence classes. Z mod 1 had 1 equivalence class. Z mod 2 has 2 equivalence classes. Okay, so the only thing that doesn't really fit any kind of pattern so far is 0, but that kind of makes sense, right? Okay, now, so what do you think about k equals 3? Sounds like a good guess. Okay, and in fact, we're going to look at k in general as long as k is a natural number. We get rid of 0 because it's irritating, right? Okay, but okay, so definition. The set of equivalence classes of this equivalence relation, equivalence mod k, is denoted by, this is really just notation, zk. Okay, so far we know 3 of these guys. So again, Z0 is kind of irritating, and I'm not going to say too much about it, but I'm going to put equals in quotation marks. So this is not mathematically precise, right? But that's just Z itself, right? Because in some sense, all it does is put each element of Z into brackets. Okay, we're not going to deal with Z0, and I won't tell you what the quotation marks around the equals are. But basically, you imagine there's a very natural bijection there, right? Every element of Z goes one-to-one onto itself sitting inside brackets, okay? So we won't deal with that much, okay? Now, Z 1, this we can say for sure, it has only one equivalence class, and that's 0. Equals Z. Now I'm sorry guys, I was right, and so this is Z containing Z. Right, so Z1 consists of one equivalence class, and that one equivalence class is just Z. So to help clarify things, Z2, that we just checked consists of 0 bar and 1 bar, and that's a set of even 2Z, even integers, and odd integers. Okay, so obviously this is going to be the way we want to think about this, right? And what do you think Z3 should be? Forget this, okay? 0 bar, 1 bar, 2 bar. And in general, what do you think ZK should be? By the way, if I go over 5 minutes, there's going to be a fire drill at 9:55 in case you haven't heard, so don't freak out when the things go off. And you're supposed to go all the way over to the amphitheater and as a gathering place, okay? Believe me, I won't be checking, okay? So, okay. Yeah, part of your grade depends on you showing up at the amphitheater that's over by near the stadium, over by Alumni Memorial, you know, where the buses collect and all that, right? Or you can go down to the lawn in front of Perkins. those are the approved gathering places. Okay, I heard sirens and that's why I got off track. Okay, anyway, okay, so it is actually just a drill. Okay, what do you think is going to happen here?
K minus 1 bar.
Yeah, K minus 1 bar. Okay, so that's the idea that each of these has K elements in it, starting with 0. And of course, well, we'll see. I could shift things around a little bit. Okay, so that's the statement of our next theorem. For any, and we're just going to focus on the natural numbers now, right? No problem there, because first of all, 0 is annoying in this context. And what do you know about, for example, Z minus 2? Well, remember, division of 2 and minus 2 is identical, right? They all divide the same things. And so Z minus 2 is just going to be Z2. You can think about that, okay? And it's going to have the same equivalence classes. So we're not going to bother about negative numbers. We're not going to bother about 0. We're just going to deal with natural numbers. N, an element of n. Zk is equal to 0, 1, K minus 1. And if m bar equals n bar, when 0 less than or equal to n less than m less than k, m equals n. Okay, so the first one is the statement that we just got there, okay? We kind of listed these guys out here, right? The second statement says that no two of these in here are the same. Okay, that we can list them all out. Remember I said there are K elements, but really this just tells you there are at most K, and maybe, you know, somewhere in here there are two of these equivalence classes that are equal. Okay, so the last one says that if we pick up, if these two are equal, then, and m and n are between 0 and k, then in fact m and n are equal. Okay? Everybody get that? That it could have been here. I mean, we know that 1 bar is not the same as 2 bar because we know that even and odd, remember we proved, every number is either even or odd and never both, okay? But we didn't prove anything like that. And in fact, that's dependent on something called the division algorithm. We didn't prove anything like that beyond even and odd, right? We didn't prove even for 3, right? That it's either, you know, divisible by 3 or it's 3k plus 1 or 3k plus 2, right? We never proved that. So there is some possibility that when we get up here that, oh, maybe 2 of these are the same, even though we wrote them differently. And this is saying that it's not true. Okay? And the proof uses the division algorithm. It's called the division algorithm even though it's not an algorithm. Okay, although it can be proved, you know, sort of as an algorithm. But what is that? That's one of the first complicated things that you learned to do when you were a young student. Well, you're all still young, right? But okay, when you were really young, okay, you learned to do long division, right? Okay, and if you were like me, you sat around doing long division all the time, okay? Yeah, okay, you probably didn't do that, right? Okay, I'm sorry to admit I did, but anyway, okay. So, but you never heard it called the division algorithm, okay? So first of all, we're looking at this, okay? So the division algorithm says that for any m an element of z, m can be uniquely written, and this is proved in one of the sections that we didn't have time to do. Okay, you'll see the division algorithm in there, and you will probably see this, you know, in your first abstract algebra course. Uniquely written as m equals k. So we've got our k here, right? Ka plus r, where 0 less than or equal to r less than k. Okay, why is this long division? Well, because r stands for remainder, right? And k is your divisor. And so this is just saying that whatever integer I pick up, I can always write it as some multiple of k plus some remainder, and the remainder is smaller than k, right? So you don't want to, when you do the division algorithm, right, when you did division, the thing that you ended up with was always smaller than the divisor, okay? And that was your remainder, okay? So the remainder should be smaller than the divisor or you haven't divided out enough. That's the way to think about it, okay? And so this should be completely clear. I mean, you know, the Greeks understood this and they just thought about it as lengths and things, you know, kind of like Archimedean principle with a remainder, okay, is basically what it is. Okay, and you want to go far enough out till the remainder is smaller than your divisor. Okay, and what may not be so obvious is that it can be done uniquely. Okay, that requires a little bit of work, and again you see uniqueness coming in. Okay, but anyway, that's what the division algorithm says, and this makes this very easy. Okay, because this part is divisible by k, right? So then if we kick the r over to this side, m minus r equals k, let's see, yeah, also I should say r and a are integers. Okay? Okay, Ka, where a is an element of z. And so what is that saying exactly? That m is equivalent to the remainder. Mod k. Right? Because the difference is a multiple of k. So in other words, whatever m you pick up, you do the division algorithm on it, it's equivalent to its remainder. And where's the remainder? The remainder is 0, 1, 2, 3, 4, 5, 6, all the way up to 1 less than k, which is k minus 1. Okay? because it's an integer, right? And it's in that range, so r equal 0, 1, all the way up to k minus 1. So everything is equivalent to something in this range here. So that shows that at least it's equal to this set, right? So the only question is, what if m and n are different, right? So everything is equivalent to something in here, right? So what if m and n are different? Well, so let's look at this, right? So proof of this statement. By the way, I'm missing a sentence or something in the proof of this in the text, so it's probably worth paying attention. I was looking at it, I thought, what? I haven't proved anything here, and then I realized there's something missing. Okay, so don't know how that happened. Okay, but anyway.